Okay, in the last video, we talked about vapor pressure depression as one of the important colligative properties. In this video, we're going to focus on boiling point elevation and freezing point depression, and we're going to learn how to figure out by how much is the freezing point going to go down in a solution, or by how much the boiling point is going to go up in a solution. Remember, solutions always have a higher boiling point than the original pure solvent. Solutions always have a lower freezing point than the original pure solvent, okay? There are two equations that we're going to be using. The boiling point elevation one is the delta TB is equal to KBM, M being molality of the solution. KB and KF, these two things, these are constant. These are molo freezing point depression constant and molo boiling point elevation constant. You can get those from this table over here. This is table 12.3 in your textbook. Again, in the ebook, it should be the same table, table 12.3. All right, so if you look up the constant, and basically these constants are related to the solvent. So each solvent has a specific constant. So you look that up, and then you write down or you calculate the molality of the solution. You multiply the molality of the solution by the constant. The constant is in degrees Celsius molal. So molality cancels, and then you end up with degrees Celsius. That will give you by how much the boiling point will go up, or by how much the freezing point will go down. So in order to find the final boiling point, you have to add that amount to the original boiling point of the pure solvent to get the boiling point of the solution, or subtract that from the pure solvent freezing point to get the freezing point of the solution. Now, these two are specifically for solutes that are non-electrolytes, meaning any covalent solute. The minute you have an ionic solute, though, that ionic solute, if it's soluble in water, is going to break apart into ions. So it causes more particles of solute. And remember what I told you in the last video. Colligative properties are affected by the amount of particles. So if you have an ionic solute, you have more particles because, let's say, a sodium chloride will break apart to form a sodium ion and a chloride ion. So now you have two particles. If you have a glucose, it's just one particle because it's a covalent compound. If you have a calcium chloride, CaCl2, you now have three particles. You have a calcium and two chlorides. So the number of particles has to be taken into account if you have an electrolyte. So when you have an electrolyte, you have to add in a Van 't Hoff factor. That Van 't Hoff factor is I. So I is basically the number of ions. So I would be 2 for sodium chloride and 3 for calcium chloride and 4 for aluminum chloride. Why? Because aluminum is 1 ion and then you have 3 chlorides, so you add it up, that's 4. So you add this I in here. So you multiply, it would be KBMI, KFMI. This is if you have an electrolyte, all right? So the first few problems we're going to do are going to be with non-electrolytes, and then I'll show you what we do with electrolytes. All right, but you get the idea here. This is what you. So a lot of it is just making sure you know how to find the molality, because you're going to need to find the molality and then plug and chug into this equation. Now, this first one I'm giving you already has the molality given, so making your life easy. So here's the question: what is the boiling point of a 2.50 molal glucose C6H12O6 aqueous solution. AQ is telling you that your solvent is water. Okay, so we need to look up the KB of water. And from the book here, water's KB is 0.512. So KB of water is 0.512 degrees Celsius molar. So how do I solve this? Delta TB is equal to KBF. I have my KB, 0.512 degrees Celsius molar. I have my molality, 2.50 molar. Remember, the glucose is just to tell you that this is a non-electrolyte. We don't care about the identity of the solute. You get your KB and KF values from the solvent. We only care about the identity of the solute if it's an electrolyte, and that way we need to figure out how many ions we're dealing with. But right now, this is a non-electrolyte, so we don't use the I. So all you do is take your 0.512, multiply it by 2.5, and your answer is 1.28. So delta TB is 1.28 degrees Celsius. So what is that telling us? It's telling us that the boiling point of this solution is elevated by 1.28 degrees. So what is the actual boiling point going to be? Well, normally pure water is 100 degrees, right? So if it's not pure water now it's a glucose solution, it's going to go up by 1.28. So you take 100 plus 1.28, the answer is 101.28 degrees Celsius. This is the boiling point of the solution. What did I do? I added the delta T to the normal boiling point of the pure solvent, which is water. Okay, so that's that one. Let's do another one that has a little bit more to it. All right, should I do this one here? Okay. All right, let's do this one. All right, so now I'm going to do a freezing point depression of a non-electrolyte also, okay? So calculate the freezing point of a solution that contains 8.50 grams of benzoic acid. Benzoic acid is C6H5COOH, written in organic chemistry style. This is benzoic acid. Why is this organic chemistry style? They're putting the carboxylic acid separate from the rest just to show everybody that this is the acid part. So that contains 8.50 grams of benzoic acid in, remember keyword in, so this is the solute, the next one is the solvent, in 75.0 grams of benzene, C6H6. So the benzene is the solvent, the benzoic acid is the solute. We want to know the freezing point. This is my neighbor's dog barking. I don't know if you can hear him. So I think I'll shut this. Luca, be quiet. I'll come see you later. All right, sorry about that, guys. All right, so when we're looking up KF, what do we look up? We look up the KF of the solvent. Remember, we don't care about the identity of the solute unless it's a non-electrolyte, and the only reason we would care is for the I value. Now, benzoic acid is a non-electrolyte. This is an organic molecule, so we don't have an I value here. Okay, we're going to look up the KF for benzene. KF for benzene is 5.065. So Kf, this is for benzene, is 5.065 degrees Celsius molar. So delta Tf is equal to Kf molar. So we have the Kf, now we need the molality. So we want the molality. How do we get molality? Remember, molality is moles of solute divided by kilograms of solvent. So which ones are solute? The benzoic acid. So what we need to do is use molar mass to convert our 8.50 grams of benzoic acid to moles of benzoic acid. And then we need to convert our grams of benzene to kilograms of benzene, right? So go ahead and do all that math. You will end up with 0.929 molar. Hopefully you guys get the same answer. What do you need to do? You need to take this, you need to get the molar mass of benzoic acid, C6H5COOH, add up the carbons, oxygen, hydrogen, molar mass, and convert your grams to moles, and then divide it by 0.075. Why 0.075? Because this is your solvent, and this is in grams, and you want to make sure you convert it to kilograms. Okay, so we have the molality, we have the Kf, we can get the delta Tf. Delta Tf is Kf times molality. If you take this and multiply it by this, let me get my calculator because I did not do the math here. All right. 0.929 times 5.065, and I have 4.71 degrees Celsius. So I'm going to go and subtract 4.71 degrees Celsius from the freezing point of pure benzene. What is the freezing point of pure benzene? You can find it in this table also. This table says that the freezing point of pure benzene is 5.455. So 5.455 minus 4.71. Okay, I got that 5.455 from the table 12.3. So 5.455 minus 4.71. Why am I subtracting? Because remember, this is a freezing point depression. It's going down. So this solution is going to freeze at 0.745 degrees Celsius. Okay, everybody see that? If this was, if the solvent happened to be water, we know that water freezes at 0 degrees Celsius. So the solution would freeze at 0 minus whatever the delta T is for the freezing, the thing that depresses the freezing point. And so all solutions are going to freeze. If it's an aqueous solution, they will all freeze at negative something. It will all be below 0. Okay, good. In the next video, I'm going to show you how to do this, but using an electrolyte. So we're using the I values, the Van 't Hoff factor. And then I will also show you how to figure out the molecular weight of an unknown compound using freezing point depression, which is exactly what you guys are going to be doing in the last lab of the semester. Okay, good.